What if I told you that simply learning something about the universe can permanently change it? Not like metaphorically, not philosophically, but physically. You see, in quantum mechanics, observation isn't passive. It's not looking, right? It's interacting. And interacting leaves a mark. See, we tend to talk about the observer effect like it's mystical or vague, but it's actually one of the most concrete, experimentally verified ideas in modern physics. The moment that you extract information from a quantum state, you alter its state. Not because reality is fragile, but because information is just never free. I'm Jesse Welch, and for legal reasons, I'm not allowed to finish that sentence. This, however, is the Quantum Observer. It's a show where we strip quantum mechanics down to what it actually says. We translate that into the logic of quantum computing, and then we ask the only question that really matters. What does this mean for the machines we're building? And what are they going to reshape? Today's episode is about the observer effect. It's awesome. Not the pop science version, not the consciousness version, like the actual literal real one, right? We're going to look at what physicists mean when they say observation and why measurement necessarily disturbs quantum systems, how this shows up in real experiments, and also why every quantum computer on Earth is designed to delay observation for as long as possible, because in quantum mechanics, the fastest way to break your computation is to look at it too soon. Let's start with the observer effect, what it actually is and what it's not, because it's not just another word for collapse. How did physicists figure out that measuring reality actually changes it? See, the observer effect wasn't discovered because physicists were trying to be philosophical. It showed up because their experiments stopped behaving. At the start of the 20th century, physics was built on a very simple assumption. You could measure a system without fundamentally altering it. You might disturb it slightly. You might introduce a little error. But in principle, the system had definite properties, whether you looked or not. See, that assumption, it works very beautifully in classical physics, in the deterministic universe, it's sometimes called. You can measure the speed of a car with a radar gun without changing the car's speed. You can weigh a brick without altering the brick. But when physicists began probing nature at atomic scales, really, really small stuff, that assumption broke down. The first cracks kind of appeared with experiments in light and electrons. To see something very small, you need a short wavelength light. You need high energy photons. And when these photons interact with an electron, they don't just report back. They transfer momentum. In other words, the act of measurement physically kicks the system. I say this all the time. In order to measure a photon, you have to absorb it. Werner Heisenberg, he formalized this in 1927 with what we now call the uncertainty principle. It was not a statement about human ignorance or how I feel about my interactions with women. It was actually a statement about physical limits. If you measure a particle's position very precisely, you disturb its momentum, not because your instruments are bad, but because interaction required to gain that information changes the state itself. This was the first serious indication that observation isn't passive at a quantum scale. It's invasive by definition. But the observer effect, it became impossible to ignore with interference experiments, especially the double slit experiment. That's the famous one. That's the cool, sexy one. When particles like electrons or photons travel through an apparatus without being measured, they produce interference patterns. See, these patterns only make sense if the particles exist in a superposition of possible paths. The moment physicists tried to determine which path the particle took, the interference vanished. Instantly, not gradually, just instantly gone. Same particles, same setup. The only difference, information was being extracted. The experiment was being observed. This told physicists something that was, at the time, deeply uncomfortable and very profound. It's not disturbance alone that matters. It's information acquisition, or information acquisition is disturbance. Even so-called gentle measurements designed to minimally perturb the system, they still destroyed interference once, which path information becomes available anywhere in the environment. By the mid-20th century, this forced a rethinking of what measurement actually is. Measurement's not just a readout, especially not in quantum physics. It's a physical interaction that entangles the system with the measuring device. The observer effect, properly understood, is not about humans watching experiments. It's about quantum systems becoming correlated with other systems, detectors, photons, fields, environments, whatever, in a way that irreversibly records information. And once that information exists, even in principle, the system can no longer behave as if it were isolated. So this realization sets the stage for everything that follows in quantum mechanics, from decoherence to quantum computing all the way to some of the stuff we're doing today. Because once you accept that information changes physical states, a new question becomes kind of unavoidable. If observation destroys quantum behavior, how do you build a machine that relies on it? That is exactly the problem that quantum engineers are solving today. So next, we're going to get precise about what measurement actually means in physics and why observation doesn't require a human being at all. So what observation means and what it definitely doesn't. Does the universe really care if you're watching? When people hear the observer effect, they jump to the wrong conclusions. That reality is waiting for a conscious mind to look at it. That idea is popular and it is very sexy. That's like the Marilyn Monroe of mixing science ideas with philosophy ideas. It's dramatic, it's popular, it's Zendaya. However, it's wrong. So it's not Zendaya. You see, in physics, observation has nothing to do with awareness. So no consciousness required, no mind over matter nonsense. Observation in quantum mechanics means something a little more specific. It means a physical interaction that extracts information. That's pretty much it. So if a system interacts with another system in a way that records information about its state, an observation has occurred, whether or not a human ever sees the result. A photon hitting a detector counts. An electron interacting with a measuring field counts. A stray molecule from the environment colliding with a quantum system, holy crap, that definitely counts. Even a dust particle can be an observer, as long as it becomes correlated with the system, which is why those quantum computers, they get cleaned relentlessly between each time they get used. Now, this is a critical distinction because it reframes the entire problem. The observer effect is not about perception. It's about entanglement, which I'm going to get to. I'm going to do a whole episode on because that's really cool. But when you measure a quantum system, you don't just read its state. You entangle it with the measurement apparatus. Before measurement, the system exists in a superposition, right? It's a coherent combination of possible outcomes. After measurement, that coherence is gone from the system that you care about. It's not because the universe chose a result for philosophical reasons. It's because the system's information is now spread across many degrees of freedom. This is why physicists say that measurement is irreversible, because once the information leaks into the environment, into detectors, electrons, thermal noise, photons, you can't put it back together again. You got to start over. And this is where people often confuse three different ideas. Measurement disturbance, which is the physical back action of interaction. Decoherence, which is the loss of coherence due to environmental entanglement. And wave function collapse, which is a mathematical rule that's used to update probabilities after measurement. They're related. They're really similar, kind of, but they're not the same thing. The observer effect kind of lives at the intersection of those first two, physical interaction and information extraction. You don't need collapse as a metaphysical event. You definitely don't need consciousness. What you need is coupling. This matters enormously for quantum computing because a quantum computer, it only works as long as its qubits remain unobserved in this like technical sense. The moment a qubit leaks information to the outside world through noise or heat or unintended measurement, it starts behaving classically, right? And the coherence is over. The system collapses. This is why quantum computers are isolated and they're shielded and they're cooled to absurd extremes. It's not because they're emotionally fragile, not like me. It's because information is dangerous. Every unwanted interaction is an accidental observation. And every accidental observation, it destroys the very quantum effects that we're trying to exploit. So when physicists say, don't observe the system yet, I don't know how often they say that, but if they ever do say that, what they really mean is don't let it talk to anything else. And this leads us directly into our next question. If observation is just interaction, how does the universe decide which interactions matter? This is where decoherence enters the story. Why does a quantum computer stop working the moment you look at it? In a classical computer, reading the result is trivial. You check a bit, stays a bit, right? Nothing breaks. In a quantum computer, reading the result is a violent act. Not metaphorically, well, maybe metaphorically, but literally, physically. A qubit stores information as a coherent superposition of states. As long as the superposition remains isolated, quantum logic can operate inside it. But the instant you measure a qubit, the very instant, you force it to interact with the outside world. And this interaction entangles the qubit with a detector. Not exactly entangles like the entanglement principle, but the detector entangles with electrons, right? The electrons entangle with the environment. And at that point, the computation's over. This is what readout really means. Quantum readout it's not exactly looking at a value. It's extracting classical information from a quantum system, which destroys the quantum state in the process. In superconducting quantum computers, for example, readout works by coupling a qubit to a microwave resonator. The qubit shifts the resonator's frequency slightly depending on its state. You send in a microwave pulse and you measure how it comes back. Now, that pulse carries information about the qubit, but it also carries away coherence, unfortunately. Once that information escapes into the classical world, there's no undo button. And this is why quantum algorithms, they delay measurement until the very end. Also because any measurement is the very end, but they delay it as long as possible. They don't sample intermediate results. They don't check progress. They don't prepare a state. They carefully manipulate interference. And only when the amplitudes have been shaped to favor the correct outcome do they measure, just once. Measurement, it is the final act. Measurement is the finish line, whether you like it or not. If you move the measurement up, you're moving the finish line up to the runner. It's not necessarily always the other way around. This is why quantum error correction is so hard. You're trying to detect errors without learning too much about the state itself. You want just enough information to correct the mistakes, but not so much that you accidentally observe the computation into oblivion. And that balancing act, extracting information without destroying coherence, it is one of the central engineering challenges of quantum computing. So it's like currently one of the boss level in quantum computing. So when people ask, why can't we just peek inside a quantum computer when it's running? The answer is simple, because peeking is a problem. Peeking is the problem, actually. And once you understand that, the observer effect stops being mysterious, starts looking more like a design constraint. If observing a quantum system destroys it, how do quantum computers work at all? Here's an uncomfortable truth. The observer effect is not a philosophical footnote in quantum computing. It's one of the core engineering constraints, actually. Every time a quantum computer produces a result, it has to measure qubits. And measurement is not passive, as we said earlier. It is a physical interaction that pushes information out of the quantum system and into classical hardware. Cables, amplifiers, detectors, memory, eyeballs. That interaction, it always comes with back action. In practical terms, reading a qubit means coupling it to something much larger and much noisier than itself. In superconducting systems, that's a microwave resonator. In trapped ions, that's scattered photons. In photonic systems, it's detectors that irreversibly absorb the particle. And once the coupling happens, the quantum state's done. Coherence is gone, computation's over, time to measure. This is why quantum engineers obsess over measurement strength, right? Measure too weakly, the result is noisy and unreliable. Measure too strongly, and you disturb the system more than is necessary, and you actually inject excess noise and error, right? So there's this trade-off that exists when you're trying to solve this problem. Information gained versus damage done. So, it shows up everywhere in hardware design. Readout fidelity actually limits how confidently you can trust an answer. This is why quantum error correction is like a major, major part of the field. Measurement back action limits how often and how precisely you can check intermediate states. Amplifier noise sets a floor on how gentle measurements can be, even with perfect control. And here's the part that's easy to miss. Improving measurement is oftentimes harder than improving gates. Like, you can make gates faster. You can optimize pulse shapes. You can add shielding. You can always add shielding. But measurement requires crossing the quantum to classical boundary every time. It just has to be, right? That boundary is just fundamentally lossy, if that's a word. If it's not, let's make it. Sounds made up. I guess all words are made up. Anyways, this is why many quantum systems delay measurement until the very last moment. It's not because it's elegant. It's just because every observation is really expensive. So when you hear about quantum hardware roadmaps, remember this. Measurement, it's not an afterthought. It's actually a bottleneck. So why does any of this matter if you're not building a quantum computer yourself? Well, it's because the observer effect, it quietly, very loudly actually, it determines how fast quantum computers can become commercially useful. Every real-world quantum application, chemistry, optimization, cryptography, materials, whatever, they depend on running circuits deep enough to extract meaningful information before measurement destroys the computation. Measurement's expensive, right? The observer effect, it has limits. How many operations you can perform before readout, how accurately results can be extracted, how much error correction overhead is required, how often results must be sampled in order to build confidence. This translates directly into cost, scale, and timelines. For example, like if readout fidelity is low, you don't just get worse answers. Like, you need to rerun the same computation like thousands or millions of times to average out the noise. That increases cloud compute costs and it limits throughput, which is why, again, error correction, big deal, much cheaper. If measurement back action is high, error correction becomes more demanding. That means more physical qubits or per logical qubit, sometimes orders of magnitude more, which slows down deployment and it raises capital requirements and it pushes back commercial viability. This is why many of the most important breakthroughs right now are not in flashy algorithms. They're in boring sounding improvements in readout chains and amplifiers and measurement protocols, like things like quantum non-demolition, QND, sometimes it's called, better cryogenic amplifiers, faster and cleaner qubit readout, smarter classical quantum control loops. These advances, they don't make headlines, but they do move timelines. So from an investment perspective, this creates a clear separation between hype and substance. Companies that can demonstrate higher readout fidelity, lower measurement-induced error, scalability, repeatable measurement pipelines, they're meaningfully closer to monetizable quantum advantage than those who simply add qubits. Like, it doesn't matter if you have 1 billion qubits if your error rate is way too high. This is also why near-term commercial quantum value tends to appear first in hybrid systems, where quantum processors, they do small, well-defined tasks, and then a classical system just handles the rest, right? Measurement is the handoff point between those two worlds. And the observer effect kind of governs that handoff. So when people ask, when will quantum matter? It already matters. It matters to me. But a better question is, when will we be able to observe quantum systems cheaply, accurately, and especially at scale, right? That answer is not qubit count. The answer determines the slope of the adoption curve. So, why observation is the bottleneck? Let's zoom out a little bit, right? The observer effect, it's not some philosophical quirk of quantum mechanics. It's actually like a hard engineering constraint. Every time you measure a quantum system, you destroy the very thing that makes it powerful, which is wild. Also kind of beautiful in like a poetic way. But that single fact shapes everything downstream. How deep quantum circuits can run. How many qubits do you actually need? How expensive each computation becomes, and why progress is slower and more uneven than headlines suggest. In classical computing, observation's free. In quantum computing, observation is the bill. That's why quantum advantage, it doesn't come from bigger machines alone, although it seems like it is. And the machines are cool looking. They're like giant gold chandeliers. It actually comes from learning when not to look, how long to wait, and how to extract information with the least possible damage. If you're trying to understand why quantum timelines stretch, why error correction dominates roadmaps, or why certain companies just quietly make progress while others stall, this might be the reason. Next time, we're going to tackle, hopefully, I might change my mind, but the thing that makes this problem unavoidable. I want to talk about decoherence, which is why reality itself refuses to stay quantum very long, and why that single fact, it actually might be the true limiting factor on the entire industry. Because once you understand decoherence, you understand why quantum computers live inside those absurd refrigerators, the dilution refrigerators that get everything down to like almost 0% Kelvin, why scaling is brutally expensive, and also why real breakthroughs, they won't look dramatic. They'll just look incremental. And that's where the real story is. So here's the final piece that I want to acknowledge before I close this out. Up to now, we've been talking about deliberate observation, right? A detector, a readout, a measurement designed specifically to extract information. Here's the uncomfortable truth. In the real universe, measurement does not only happen when we ask for it. Measurement, in the definition that we came to earlier. Every quantum system is surrounded by an environment. All of these things have to live in the universe. There are thermal vibrations. There's stray protons, electromagnetic noise. There's just all these uncontrolled interactions that don't care that what experiment you're running, that you're trying to maintain superposition for, 1 more thousandth or millionth of a second longer. And those interactions, they extract information too, and not cleanly at all, and also not intentionally, but relentlessly. And that's the problem. This is where the observer effect, it quietly hands the baton to something even more important, and that's decoherence. And decoherence is what happens when the environment becomes the observer. Not a conscious one, not like us. Not a curious one either. Just a very efficient one, a brutally efficient one. It continuously entangles quantum systems with everything around them, spreading information so widely that interference becomes impossible to recover. Not because the quantum rules stop working, they continue to work, but it's because the environment has just leaked, or not the environment, but the information has leaked beyond retrieval. This is why quantum systems, they don't stay quantum for long. This is why superpositions, they don't survive at room temperature. And this is why quantum computers have to live in these absurdly isolated conditions, basically shielded from the universe that they're built inside. The observer effect tells us that measurement is irreversible. Decoherence. That tells us that the universe is always measuring. And that tension between what we want to control and what we cannot control, that's really the central engineering problem of quantum technology. Next time I'm going to unpack decoherence more properly, not as a philosophy, not as a metaphor. Hopefully I make some cool metaphors during it, but really I want to unpack it as the physical reason that reality looks classical, even though it isn't. Because if observation collapses quantum states, decoherence explains why the world refuses to stay quantum in the first place. And once you understand that, you understand why building a useful quantum computer is one of the hardest engineering challenges that humanity has ever attempted. I'm Jesse. Thank you guys so much for watching. We have a Quantum Observer newsletter. We've got a website. We're on TikTok. Pretty sure we're on Instagram. Please follow me on YouTube. Also, thank you for everyone who's been commenting, especially the negative comments. You only make me better. Hopefully, I'll be able in the future to explain some of the conversations, some of the concepts that maybe I wasn't so clear on. So don't hesitate to make a suggestion or a criticism. Just try to be kind to me. I'm very fragile, like a quantum system. But until next time, thanks for hanging out.